All right, so in this video, we are going to be covering section 3.4. We're going to talk about transformations of functions. So this section, while it does have a few more slides than most of my other videos, are pretty quick problems and a pretty easy concept to pick up on. Essentially, we're going to talk about that if we know what one of the basic shapes looks like absolute value or square roots or one of the other ones we did, if there's a basic number either added or subtracted or even multiplied to it, what does that do to the graph without having to replot points to figure that out? And so throughout this video, I'm going to cover a number of different kinds of shifts or transformations that we need to be aware of. And so our first one here is called a vertical shift of a function. And so what this essentially says is that if you are ever given a function of a graph that we know how to draw, and it either has a number added or subtracted to the end of it, this will shift it either up or down on the y-axis. And so the two differences would be is that if you have a plus c, so if you're adding like a 1 or a 2 or something like that, you're going to be shifting it upward. All right. Versus if you have a number that's being subtracted like a -4 or a minus whatever, that means you're going to be shifting downward from the original graph. And so over here on the right, you notice the little visual I gave y'all. The purple graph in the middle is our graph of an absolute value. Remember, it's a V shape. And what I've shown you here is that if you add a number outside, it shifts it up 3, versus if you subtract a 3 on the outside, it shifts it down 3. So we'll use that first idea to shift graphs vertically, either up or down based on the number that you're given. So besides an absolute value, we also talked about square root graphs. So let me do one of those. And so what you need to know here is that if you're asked to graph the square root of x plus 2, what we do remember, and I'm going to do a little dotted line here, is that a square root graph, looks something like this little dotted line I put here. But what we notice in our graph is that it has a +2 out here on the end. So from what we just went over, this would mean that you are going to have a vertical shift and you are going to have to move the original square root graph up 2 units. So instead of starting at the origin at 0, 0, we're actually going to start here at 2, and we're going to draw the exact same shape. Do not deviate from that. So it will look something like this. And so I'll keep the dotted line there just for reference of how much it shifted from the original. And so that's how you do a vertical shift of a graph that you already know the picture of. The other kind of shift you need to know how to do, maybe a little trickier, but it's called a horizontal shift. So the difference here is instead of the number being added or subtracted outside the function, it will be added or subtracted inside the function. So you'll notice that here on this first one, if you have a plus c or if you have a minus c inside your function, that does not mean you're going to shift up or down. You're either going to shift left or right. So now be careful here because this one does work a little backwards from what you would think. When you have a plus c on the inside, this means you are going to actually shift left of the original picture that you know. Similarly, if you have a minus c on the inside of your function, you are going to shift horizontally to the right. Now that is backwards from what you traditionally would think. Traditionally, we would think plus goes right and minus goes left. But with horizontal shifts only, those work backwards. So please be careful as we go through our problems in this video. So back to my absolute value and using the 3 example, you'll notice once again, there's the purple graph in the middle, which is the absolute value of x. But notice when there is a +3 inside, we shift to the left 3 units. Versus if there's a -3 on the inside, you're shifting to the right. That's because horizontal shifts work opposite of what you traditionally would think. This is the only one that works backwards, so just be aware of it. So let me give you a different absolute value graph. So what if you're asked to graph the absolute value of x minus 1? Well, first thing I notice is that this is an absolute value graph. So back to my little dotted line idea. If I were to just put a red dotted line on your screen, this gives you the idea of what the original absolute value graph looks like. But since you have this minus 1 and it's inside of the absolute value, this is telling me I have to do a horizontal shift. Now, with horizontal, we go opposite of what you would think. So since it's a minus 1, we are going to shift to the right 1 unit. So I'm going to take this entire V, and instead of the bottom of the V being at the origin, I'm going to shift it to the right 1 unit, and then I'm going to draw the exact same V that you see as a dotted line. And so that would be a sketch of what the absolute value of x minus 1 looks like. All right, so outside of shifting, there's a couple of other things we have to be aware of. The next one I think is a pretty easy one. It's reflections. And so what happens, or how do we know if a graph is supposed to be upside down? That's kind of the easy way to think of this. Well, whenever we work with a problem and there ends up being a negative in front of it, all this means is you are going to reflect the graph about the x-axis, or as most people just think of it, you are going to make your graph be upside down. And so this is one of the easiest transformations we learn. If there's a negative in the front, flip the graph upside down. So once again, to my visual, you can see in purple, you have the absolute value of x. And then if we stick a negative in the front, it's kind of hard to see, but it is there. All you do is you take that V and you flip it upside down, and that's how you deal with a reflection of a function. So a pretty easy one to do here. We'll just do one example here, and then we'll do some more in a minute. If you're asked to graph g of x equals negative x squared, well, we've learned in previous sections that x squared would be a parabola that looks something like this. Now, the difference for us is that we have this negative in the front, which means we are being asked to do a reflection around the x-axis. So all I'm going to do is I'm going to draw a picture of the same parabola, but I'm going to flip it upside down. So it should end up looking like this. And the purple graph is a sketch of g of x equals negative x squared. I think that's one of the easiest ones to do. And so there you go. All right. So my last little transformation to show you, and then we're going to combine some of these together, is what's called vertical stretches and vertical compressions. All right. So this will occur anytime you have a number that is being multiplied in front of your original function. So if you multiply it by any a value, no matter how big or how small, it will affect the shape of your graph. And so here's the two rules you have to learn with this. If the value of a is any number bigger than 1, like a 2 or a 3 or whatever, what you are doing is you are going to perform what's called a vertical stretch. And I'll show you what that is in the picture over here on the right in just a second. So we will vertically stretch the graph. If your value of a falls between 0 and 1, you're going to do what's called a vertical compression of the graph instead. And so looking at what these differences are, at my picture over here, once again, in purple is the original. I decided to do x squared because it's a little bit easier to see here. The purple graph in the middle is your normal x squared graph. As you can see by the first rule, since we multiplied it by a number that's bigger than 1, in this case we multiplied it by 3, it did a vertical stretch. So essentially you would take the graph and you would stretch it up, and really it makes it more of a narrow graph. So a word that you'll hear me say a few times today is the graph is now more narrow. It's a skinnier graph that's going up and down. Versus if you were to take another A value and let's say some number between 0 and 1. The one I use for my picture is 1/5. This is going to take it and it's going to compress the graph down. So you're kind of pushing the graph closer to each other. And what this ends up doing is it makes the graph wider. As you can see in that blue picture down at the very bottom, that's a very wide parabola. That's because you're multiplying it by such a small number that it takes a lot longer to go up. So you have to widen it out in order for it to go up in any level of certainty. So to show you how what I'm looking for you to do on your assignments is this. What if you're asked to graph g of x equals 3 times the absolute value of x? Well, once again, back to my idea. When we have an absolute value of x, a normal graph is just a regular V shape. But since we are multiplying this absolute value by an by an A value, and that A value in this case is greater than 1, this is what's going to be called a vertical stretch. And so my hint to y'all is that it should be a graph that's more narrow than the original. So if I were to take this absolute value and stretch it vertically, what will end up happening is it will look something like this. And I'm not looking for perfection, but I'm looking for a general sense of what it's trying to draw. And so on your homework, you'll see options to pick. And so you got to make sure you pick the one that becomes more narrow. So this one, since the number is bigger than 1, is going up a lot quicker than the traditional absolute value graph does because you're multiplying it by such a large number compared to 1. And so finally, just kind of remembering, here are the 4 things that we've learned in this video. We learned about horizontal shifts. We learned about vertical stretches and compressions. We learned about reflections, and then we learned about vertical shifts. And so this is not a set order that you have to do, but I've had students in the past ask me, what order do you look for these things in? So when I was going through a couple of problems on my own, I kind of wrote these down in this order. That's just how I do them. As long as you incorporate all the different transformations at some point in your picture, you will get it correct. But if you're looking for an order to go, maybe this is the way you want to do it. Do the horizontal shifts because those are tricky because they work backwards. Vertical stretches and compressions. Is it skinnier? Is it wider? Figure that out. Reflection. Is it going to flip upside down? Look for that negative in the front. And finally, a vertical shift. Should you shift your graph up or down a certain number? Look if there's a number added or subtracted on the end. And so what I'm going to do for the last few slides, I'm going to combine multiple different transformations into one, and we're going to draw these and sketch these together. So beginning with number 5 here, you have f of x equals the negative absolute value of x minus 1 plus 2. Now, before I do any of my transformations, like I've been showing y'all on every graph so far, I see absolute value. So I know in my mind, my original graph is a V shape. Now, this is going to change a lot because I see 3 different things you have to take into account for. So the first thing, I'm just going to go left to right here. The first thing I notice is the negative in the front. That means you're going to have to perform a reflection. So I know that it's going to flip upside down. Then you have this -1 inside the absolute value. This is what we call a horizontal shift. Now remember, with horizontals, that's the tricky ones. It goes backwards. So we'll be shifting this graph to the right 1 unit. And then finally, you've got this +2 on the end, which is what we call a vertical shift. No tricks on this one. It's a +2, so we will shift the graph up. So what you're going to do is you got to perform all 3 things at once here. We're going to take this original, this red dot you see, red dotted line you see here. I'm going to flip it upside down. I'm going to shift it to the right one and up 2. So let's start with the right one and up 2. So right one, up 2 would move my new point to here. But instead of just drawing a regular absolute value graph, since there's a negative in the front, I'm going to reflect it upside down, and it's going to look something like this. The green graph is our negative absolute value of x minus 1 and then plus 2. All right. So what about this one? Instead of me having you draw one that has multiple things, what if I just want you to do a very basic, here's a picture, can you tell me what happened? So according to this, it asks for the graph below was created by shifting one of the basic functions, identify the basic function, and write a new function which describes the graph. Well, when I look at this picture, immediately in my mind, I notice that this should be a parabola, which traditionally has an equation of f of x equals x squared. But I also notice that it's not in the same spot that it always is, because typically the bottom of a parabola is not over here at 5, it's usually over here at 0. So according to this picture, we have shifted to the right 5 units from where it originally starts. So how do we incorporate a horizontal shift of 5 units to the right? Well, a horizontal shift always occurs inside of the function. So I'm going to have to take x, and I'm going to have to either add or subtract 5 to shift to the right. But remember, horizontal shifts work backwards from what you're used to. So even though right 5 makes you think plus, we have to go backwards, which would make this minus 5. And so this picture to the left is a graph of the function f of x equals x minus 5 squared. You can do this for any graph I give you as long as we know what the picture is and you can tell what transformations happen. So exact same instructions. What is this the graph of? Well, just looking at the basic picture, it looks like that this is going to start off and this is the picture of a square root graph. But the difference is that this square root graph is starting at -2 when normally it starts at 0. So according to this, you have shifted down 2 units from the original spot. So that's a vertical translation. So how you incorporate a vertical translation into your function is actually a lot easier than a horizontal, because all you have to do is the 2 that's going down, we will stick a -2 on the end, and that incorporates our vertical shift. And so a little bit longer of a video in terms of slides we had to cover, but this is a pretty easy section because there's not a lot of work involved. It's more just making sure you understand shifting and different transformation aspects. So that wraps up my video for section 3.4. In the next couple of videos, we're going to move into section 3.5, which is going to talk about the different ideas of combinations of functions, and we'll also look at the idea of composition of functions as well.